Okay, we start the lecture for today. So first of all, a kind of recall, right? Recall the frequency response design of control systems. So first of all, okay, the first point that we need to recall is that there are two kinds of systems. We have the open loop and closed loop systems. The closed loop system is kind of a feedback control. And then this kind of system, the feedback or closed loop system, is used in practice. And then for the open loop system, to test or characterize the system response. It can help the design of a closed loop system. Then the system can be system or the open loop system. It can be represented in bold plots. So that is how we have the magnitude and then the angle. That those are plotted against the frequency. So the requirement for the control system we need a stability, and then we also need the small steady state array. And then we also want fast response. The small steady state error means that we need the accuracy. And then the fast response means that we want the efficiency. Okay, then the the material that we're going to cover today is largely on the design. Okay. So then let us start with the design methods. So first of all, we carry out an analysis of the steady state error. In carrying out the analysis, we need to classify the types of control systems. Okay. So generally, we have the type 1, type 2, and then type 3 systems. Type 0, 1, and 2. We have 3 types. So the types of systems is indicated by the integrators or the integration actions. It is important. So in the transfer function. So generally, we can have a transfer function so we focus on the open loop, right? Because the closed loop system response can be inferred or can be found out from the open loop response. So in general, we have a K and then S to power something, right? And then S plus AS plus 1. Then we have TBS plus 1, and then etc., etc. So we have the K is the gain, and then TS of A plus 1, that is the phase lead, and then the TBS plus 1 is the phase lag. The phase lead means that the angle increases against frequency. And then the phase lag is the opposite. The angle will decrease against frequency. And then the S term is the pure integrator or pure integration. So it is from the Laplace transform, the integral theorem. The N, okay, determines type of system. It also affects the steady state error. So why this term will affect the steady state error? We also recall the final value theorem. Okay, it says that as time goes to infinity, so it is equivalent to the limit that the S variable goes to 0. So the S is the Laplace variable. Okay, from those basic definitions, then we look into the definition of the steady state error. Then we take a look into what is the steady state error. Okay, for example, suppose we have the open loop system, which is the G of S. Then the closed loop is the response divided by the input. Okay, here we assume unity feedback. Otherwise, we have the sensor, the H terms multiplied with the G. And then for the simplest case, we assume that the sensor is a 1, so we have the unity feedback. And then we are interested in the error. Okay. So suppose we have the system configured in this manner. The feedback system, the reference, then control, and then we have the error here. This C. So we know that from this block diagram, error is R minus C. Okay, because of the negative feedback. Then if we factorize, we factorize the error into the denominator here. So this term is the error percentage given input R. And this part, so it is the transfer function. Then from the transfer function equals 1 plus g and then g, then again, then the so it is 1 minus so so we put the denominator 1 plus g to multiply with this term 1. Okay, so that we have 1 plus g minus g and then the common denominator. So it is 1 plus g. This is the error ratio. Then, of course, the absolute error, okay, it is E minus. So it depends on the type of input. And type of system. The type of input is due to R, and then the type of system is due to the transfer function C of R. Okay, agree? The error depends on the input and also depends on the system. And then again, the error, the steady state error. If we take the limit time to infinitive and then the error, so it is equivalent to, we take the limit of the s variable to 0 of the error in the Laplace domain. So it is our limit Laplace domain times the s variable. So it is the limit s go to 0, and then the s, the input, and then the open loop system. Okay. Any question up to now? Then we take a look at different cases. Okay. For example, we have the case 1, right? The input is a step function. Then the input it is 1 over s. Okay, agree that if it is a step function, then the Laplace transform of input is 1 over s. Then the steady state error. It is the limit s go to 0, and then the SR is 1 plus GS. Okay. So this 1 over s cancels with the s here. Okay. So we have 1 plus GS only. So now for the different types of system, type 0 system. Type 0 system. It is S0 in the denominator of transfer function. So the G equals K S0, and then all the J omega plus 1 S plus 1, and then TBS plus 1, etc., etc. So when S tends to 0, so we have only K S to the power 0, which is K itself. So the error of the type 0 system, so it is equals 1 plus 1 K. So for example, if K equals 1, then we have the error equals 1, 1 plus 1 equals half. It is a very big error. If K equals 10, then it is 1 plus 10 is 1 over 11. It is smaller than 0.1. Okay. If K equals 100, then the error is 1 plus 100, 101. It is smaller than 0.01. So we observe or we conclude that, okay, reduce the error or steady state error. Then you need to increase gain. Then we take a look at the type 1 system. So here we have S1, right, in the denominator of the transfer function. Then the transfer function is k is 1, and then tas plus 1, and then tbs plus 1, etc., etc. And then as s goes to 0, what we have k divided by 0, and then it is infinitive. Then the error is one plus k equals 1 plus infinitive. So it is 0 error. Okay. For this system, type 1 system, to arrive at 0 error, so we may not need to increase open loop gain. But need an integration action or integration process. This integration process it increases system from type 0 to type 1. Okay. So that at least we can see that if we want to reduce the error, there are two approaches that we can take, right? First of all, we can increase the gain, right? And then we can also put in, if we do not want to increase the gain, then we can put an integration action or integration process into the controller. Then the reason that why we do not want to increase the gain. If the gain is too high, we have to dump into a large amount of energy to drive the system. Right. For example, we need a 10 volt to drive a electric motor. If we increase the gain, then we might need 100 volt to drive the motor, or even higher. Right. Sometimes we do not want or we cannot afford the higher amount of energy to drive the system. Then we put in the integration action. Okay. So there are another then we look at the another system with the type 2 system. So similar to the previous case, we have the k, and then now this time is 2 here, TAS plus 1, etc., and then TBS plus 1, etc., etc. Again, s goes to 0, and then with g equals k, and then to 0, it also tends to infinitive. Now the error in response to a ramp function. Okay. That is the value increasing with against time, increasing with time. Then the Laplace transform is 1 over s squared. But in this case, the error is still the limit s goes to 0 and 1 plus g, and then the r is here, g of s. Now the rs is 1 over s squared, and then this term s here, we still have an s in the denominator. So as s goes to 0, then what happens? Then it depends on the type of the system. Then for the type 2 system, for the type 2 system, we have this case, the s terms goes to, makes the gain goes to infinitive. Okay. So in this case, for a type 2 system, error goes to 0. And then if we have the and then for acceleration input, so the input is t squared over 2. The t squared corresponds to the acceleration. Then in Laplace transform, So the input equals 1 over s cubed. So our steady state error is the limit s goes to 0, and then 1 plus g, and then the s r of s. Then we have the limit s go to 0, then s square of g. So for this kind of acceleration input, this kind of signal, then for the type 0 system, then s square g of s equals 0. And then for the type 1 system, then we have the s square g. So it is s square sum k and then over s. So it is s of n k. One G. For this one, let me see. Okay, it should be 1 plus s g. S squared bracket 1 plus g. Yeah. Thank you for that. So for the type 1 system, we have this, and then it also go to 0 when the s is 0. And then for the type 2 system, then we have the s squared gs, s squared k, and then for the type 2 system is s squared here. So it is k. Then we can conclude that, right, for acceleration input, so the Ts of t, and then equivalent to 1 over s cubed input. And then the steady state error is infinity for type 0. So it is 1 over k for type 0 and then type 1. And then it is for 1 over k for type 2, and and then 0 for higher types. So what we can see, or what we can conclude, is that the general input can contain a step, the ramp, the acceleration signals, and their combinations. So in order to ensure small steady state error, higher system types is preferred. Okay. Okay, agree with this. Agree with this conclusion that we need a higher type of system in order to reduce the steady state error. Okay, and then how we can make use of the Beauport. So if we have a type 0 system, the G equals S0 and then K and then TAS plus 1, etc., etc. This is a type 0 system. And then we know that for the K, the magnitude is constant. And then for TAS plus 1, what the magnitude will look like? It will look like something like this, increasing. And then at this point, it is 1 over TA. So this is the frequency axis. And then for TBS plus 1, the magnitude would look like and then this point is 1 over TB, it is decreasing. Okay, agree with this? So it depends on the numerical values of our TA and B. The resulting magnitude curve will be different. So, but for omega much smaller than 1, or the low frequency, then K dominates. And then it determines the steady state error. So it is the K itself. Then we can see that for a type series system, the type series system, typically we have the 20 log 10K somewhere, right? And then depends on the frequency. For example, this could be 1 over TA, this could be 1 of TB, or etc., etc. Then we can find out or read off from the plot. Okay, we can read from both plot. And then we calculate K. The K equals 10 to the power, for example, this equals so many dB, right? And then it is so many decibel divided by the 20. Okay, and then gives us the steady state error. For the steady state error, for example, equals 1 plus 1 plus K. It is a unit step input. So we can make use of the bow plot in this manner to find out K, and then we can infer the steady state error. Then for a type 1 system, so we have G equals K S to the power 1, and then TAS plus 1, etc., and then TBS plus 1, etc. So for the K, it is again it is constant magnitude in both plot. And then for TAS plus 1, and then we see that it is increasing. And then for TBS plus 1, so it is decreasing. And then for 1 over S, okay, it is a ever decreasing. And then particularly at this point, equals 1, and then it is 0 decibel. So because of the 1 over S term. That is the type 1 system. We can see that the total Bow plot somewhere at the low frequency. This is a low frequency. And then at some other frequency, it may change like this. It may change like this or whatever. Depends on the other terms. Okay, this one may be one of TA, and then this one of TB. All depends on the numerical value. But for the lower frequency term, so this term in particular, it is minus 20 decibel per decade. Then at the low frequencies, so approximates the G equals K of J omega only. Then what we can do, we consider at omega equals 1 can read off from Bow plot. The value of K. Then depends on input signal. Then we can find the steady state error. Okay, what we can see here is that the shape, the shape of Bow plot is related to type of system. So very similarly for type 2 system, we have the G equals K and then S square this time, and then TAS plus 1, etc. and then TBS plus 1, etc. And then due to 1 over S term, or S square term, then at low frequency, the magnitude plot, this loop is minus 40 decibel per decade. Then we have the Bow plot like this. So omega then may change like this, and then may change like this. Depends on the value of the TA and TB constants. Here, this slope is minus 40 decibel per decade. So somewhere, or extension somewhere. So this point could be omega equals 1 or somewhere. It depends on all the numerical values. Again, at this point can go rid of with K from blue plot and find steady state error. Okay, we can see that we can conclude that the shape of bow plot in particular at low frequencies can determine the steady state error. Okay. So irrespective of the actual numerical values of all the other terms, we a kind of a standardized, well, it is standardization that we rid off the gain at omega equals 1. So it is just one thing to pay attention to in practice. And then for other systems, type 3, type 4, or whatever, right? We just increase the slope from minus 20 to minus 40 to minus 60, etc., etc. Then we can find it out. And then this is one of the use of the bow plot in the system design. Okay, then I think we should take a break, right?
Just asking if you are going to continue lecture for the rest of tutorial.
The next hour is tutorial.
Tutorial, all right. So I take that back. All right. Thank you so much.
Hi. Just have a question about this file. So, does this 0 come from the final value here? Right? Yeah, just for this bit. For acceleration.
For acceleration. For acceleration input, we have the error is defined like this. Agree? Because of the one escape. So we have the error with the S squared term. So I can type an error here should be 1 plus GS.
Yeah.
And then, circle limit. So for the type 0 system, for the type 1 solution of the G does not contain any S
On the bottom. So it'll be like.
Should we do it on the
Yeah, sure.
I was just reading the words. I don't know if that happens, Mark, but I'm pretty sure it's a region of acceptance.
Because when I got it there was December, so when I left, I assembled it again. I thought Zoran told you that it was I told Zoran to tell me that it was Bruce
I was just once if I went through this.
thought it was a complex question.
Because the assignment is like, yeah, 8 plus 5 marks.
Oh, okay.
So I assume it's another 2 marks for attendance and yeah, so it's 15% all up.
I'm not mad. Like, I don't know.
So the lab part itself, like, whereas everything else was like,
Fair enough.
right, just like, you know, you're going to class.
One person asking 8 plus 5, the other person is so confused by this. What's wrong with that?
Doing these calculations.
Why? Because it's too simple. Yeah, you can. Oh, but do you understand what this is?
Yeah, 13 is the answer.
Correct.
Where you had said to make the system critically dense, then you ask the students to make zeta equal to 1 over square root of 2.
Was it? I changed the.
So if critical damp is required, suggest how to change the spring and the damper to produce the
I think I've changed that. I think I've removed the critical damp.
Oh.
In a newer version.
The point of surviving is just so you can eat the next day. Like, you can eat and survive. As long as you eat.
And also sorry here, after we solve the solution, we want to say that the phase margin is 50 degrees, yes? But finally in the border plot, the phase margin of the modified system is 13.9. So we have solved it for students to make it 50, but when we draw the border diagram, it says it is 13.1. So this one, sample 1, 2.
Let me take example 2.
still don't understand that one.
What do you mean?
Because you mean this one? How could this be? But this one is generating automatically. H2 minus HD minus H2 is automatically generating error. This one is what we want to minimize. So you use something to compensate it. But you just get this signal here because I know you can test this one. What do you mean generating? I mean, this signal is input to compensate this error.
We define what A1 is as one. Because just imagine this system. No, just imagine this system has any voltages or anything. To maintain the system, we have to have some sort of dispensation. And then probably the
It should be A times H2 minus because we need
then still going to be H2 minus H2 plus something.
yes, because when you go yeah, A times E minus H2.
HD is bigger than H2. So it puts more in. It's like, if the signal is here, we make it go up. H2 bigger than HD. Also equals it. We set it as because you stop. Just set it so that it trips. That is where the like if that was
like that in somewhere where I had good points already. It makes sense.